So far in section 5.1, we learned the definitions and basic rules of probability. And then in 5.2, we learned about disjoint, also known as mutually exclusive, and the addition and complement rules. So we want to go from there and we want to kick it up a level to talk about the independence definition and multiplication rules. So let's think about independent. Two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Okay, so first of all, it doesn't have to just be two, but it's just easiest to explain with two. And you know a lot of things that work like this. So there's a lot of probability experiments that are independent. So for example, craps, right? Dice games in general, actually just dice in general, right? Dice games are independent. Every time you pick up that die, it doesn't have any memory. So having rolled a 7 last time does not affect the chances of rolling a 7 next time. Roulette. Roulette is independent because every time you spin, the wheel has no memory of what it's rolled before or what it's chosen before, right? So it every single time you spin that wheel, it's independent. Speaking of which, the Wheel of Fortune in the TV show The Wheel of Fortune, that's independent. Every time you spin the wheel, the giant wheel that they spin in The Price is Right on television, that's independent. Doesn't matter what the last person spinned, you have just as much likelihood of getting a spot as anybody else. Lotteries. A lot of lotteries are independent. Just because you won on the last scratch off card doesn't affect your winning on the next scratch off card. A lot of times they have, a bin for the first number, 10 numbered balls in the first number, 10 numbered balls in the second bin for the second number, and so on. So a lot of those are independent. Dependent is when one thing affects the next. So when you draw the first thing, or when you pull the first, or you win the first round, or whatever, it affects the chances of you winning the next round. So card games are kind of classic for this, right? So when you dealt a card, it affects what's left in the deck. So card dealing, right? Instead of roulette, how about bingo? When you play bingo, right? So they'll pull a number out of the thing. They'll say, N22, N22, and then it's left aside and it won't be drawn again, not for that round. So that's dependent because what's being drawn is affecting what's left in the bin, right? Now, game to game wise, bingo is independent because it doesn't matter if you won last time, right? Your chances of winning the next time are equally likely as long as you're paying attention. But while you're playing that round of bingo, every, G17 that comes out is affecting what's left. And then gumballs, my favorite. When I was a kid, we would leave the restaurants and they'd be those beautiful gumball machines, and I'd want a red one because they always tasted the best. And so if I put a quarter in and I get a blue one out, that's affecting the chances of the next person getting a red one, and so on. Because once the gumball's out, it's not going back in. All right, so let's think about this. Well, card dealing, I just said card dealing was dependent. It is right here. So card dealing is dependent because you want to be dealt an ace, that's first, and then a king, that's second. Well, that would be very much dependent because being dealt the ace affects what's left in the deck, the gumball machine of cards, as it were. Right? So that would be dependent for sure. All right, you're dealt an ace. You replace the card. Oh, that's interesting. If you replace the card, as long as you're not playing against a magician or something, my public service announcement of the day is don't play cards against magicians. They're usually pretty good at finagling those cards and cheating. But as long as you're not playing against a magician or a card shark, you should be fine, right? It should be independent because you replaced that first card drawn. One assumes you probably shuffle as well there. All right, now what about this one? A JC student is chosen at random. The student is in their first year at JC and the student is less than 20 years old. Now you might be thinking independent. People could be any age and I get what you're thinking, but no, it's actually dependent. And here's why. If I know that the student is in their first year, if I see them in my class and they say, hey, I'm in my first year at JC, then the chances of them being 35 years old it's not non-existent. It's, they could be 35, but the vast majority of students that are in their first year are under 20 years old. Right? So it's a much larger group of under 20 first years than it is 35-year-old first years, right? So because of that larger group, we know that if I know that they're in their first year, then they're much more likely to be under 20 years old, right? It's not that people over 20 can't be in their first year, but it's much less probable, right? And that's, again, because the under 20 group is so large at the college. All right. Now, you don't want to get this confused with disjoint, which we learned about in section 5.2. Events are independent if the occurrence of one does not affect the other. That's usually referring, though not always, but it's usually referring to a multiple events in sequence. Now, not always, for example, for this student example right here, that's not really a sequence of events. I mean, it sort of is, because you kind of imagine them telling you that they're in their first year first, but it doesn't have to be that way. But these other things up here, yes, you're definitely getting one and then the next and then the next, right? So independent is usually referring to this thing happened, then this thing happened, then this thing happened. It's sort of like talking to a 7-year-old trying to tell you a story, right? And then this, and then this, and then this, right? And you just keep following along. So that sequence piece, that's important, right? You're talking about one after the other after the other. Disjoint was not doing that. Disjoint was talking about the occurrence of multiple events at the same time, right? When the occurrence of one affects the other so much that it makes it impossible. So, for example, if I toss a die just once, what's the chances it's a 3 and a 4? Well, it can't be both. It's either a 3 or it's a 4. Those are disjoint. If I toss the die one after the other, could I get a 3, then a 4, then a 5? Sure, that would be independent because dice in general are independent. Dice have no memory of what they've tossed before. All right, so let's choose a student from class. The student, we're going to determine whether these are disjoint, independent, or neither. So if you choose a student from class and the student is a senior, then the student is a junior, well, that's kind of obviously disjoint, right? You can't be both. Either you're a senior or you're a junior, but you can't be both at the same time. And it's one student. Did you notice the a student? That's singular, right? So since it's a student, right, a single student cannot be both at the same time. That's called the definite article. A definite article lets you know exactly how many there are. That's an English term, right? So it's a single student implied cannot be both at the same time. So that's disjoint. Now, a student is chosen from class. The student is a woman and the student is in a sorority. Okay, again, it's a single student. So you might be thinking, all right, disjoint, not disjoint. Well, it's not disjoint because sororities are made up of women. So she could be in both. So that's definitely not or okay. Now, what about independent? Now, don't get into the idea of like she could be independent. She's an independent girl. She can, do what she wants. That's not the same thing. We're not talking about psychological independence. We're talking about a probabilistic independence. So if you look at a classroom full of students and you think, what are the chances they're in a sorority? Well, if you know they're a woman, then you know that their chances of them being in a sorority have gone up, obviously. Or think of it this way. Suppose I look at a classroom full of students and I think, what's the chances, what's the proportion of these students that are in a sorority? And then I ask all the male students to leave, go take a break. And they all get up and leave and only the women students are left. What happened to the chances of being in a sorority in my class? Let's say with all the guys in there, it was, 15%. But once they walk out of the room, all of a sudden, it flies up to 30%. Because half the class was guys. Well, then exactly. If you know the student is a woman, then you've changed the probability of them being in a sorority. Think of it this way. If you knew the student was a man, the chance of being in a sorority is basically 0 unless they're in one of those bad Adam Sandler movies. Exactly, right? So if it's affecting it that much, then it's got to be that it's dependent. So it's actually neither. It's not disjoint because a woman could be in a sorority and a woman at the same time. And it's dependent, right? Not independent. So I guess I could say dependent. because sororities are female organizations. So once you know the student is female, that affects the probability of them being in the sorority. Now, why does this all matter so much to us? Well, because we have some multiplication rules for independent events. So this will be probability rule number 4 in your appendix packet that you're given to you on your test, and rule number 5. They're both for independent events. It's just that number 4 is for only 2 and number 5 is for multiple. Technically, they're the same rule. Number 4 is just like a special case of number 5. So we have the following table shows the number of graduates from JC from spring 2010 to winter 2011 by degree. Assume that the degree types are independent. All right, so there they are. I'm going to select 2 JC graduates at random. What's the probability that the first one is an associate in arts and the second one is a certificate? Now you'll notice right up here it says assume the degree types are independent. You're selecting 2 JC graduates at random. You're assuming that one does not affect the other, right? One student's major choice does not affect the other. So the probability the first student is associate in arts is 0.0613, and the second student being certificate is 0.2117. Since they're independent, all you have to do is multiply those 2 numbers, and you'll have your final results. So I want the first one to be associate in arts, the second one to be certificate. So that's the probability of the first one being associate in arts, second one certificate. 0.0613 times 0.2117 gets me 0.01298. And if you don't believe me, I can pull up the calculator. So there it is. Great. Well, this wasn't difficult. You just multiply, right? And that's all the multiplication rule for independent events is. That's why they're independent events. They're a lot easier when they're independent, trust me on that, than when they're dependent. Dependent is section 5.4, which is quite tricky. All right, so continuing with this same theme, suppose we look at 2010-2011 graduates. You're selecting 3 random graduates. What's the probability that all of them are AAS? Oh, let me change my color coding a little bit here. One second. All right, so example 3 is the pink one. And now I want to talk about associate and applied science, which is this column or this row right here. So I want to make that a different color, like, I don't know, green or something. All right, so the way this rule works is it's basically just an expanded version of the other rule. You just multiply the probability of the first person being AAS, Associate in Applied Science, times the probability of the next person's Associate in Applied Science, and the third person, same thing. So that's the probability of an Associate in Applied Science to the third power, right? Because you're going to take, so you can either write it out like this, first person, second person, third person, or you can just say, hey, it's all the same for these 3, so I'm just going to take that to the third power, which is 0.4745 to the third. And there you have it. So it's 0.1068. Now the thing to notice about the multiplication rule, couple things before we leave this page. 1, this is way better to find probabilities than a tree diagram. So much better. For one thing, we didn't have to make a terrible tree diagram with all of the branches and figure everything out. We didn't have to do any of that. We also didn't have to assume equally likely. So that's nice. So we didn't have to do the whole like everything's got an equal chance, because they don't. An associate in applied science was actually much higher than the others in the group, right? So that's really nice. And the fact that we can do this with really large sample spaces, where a tree diagram would just be a nightmare. I mean, we weren't even enjoying them for 2 or 3 different trials, right? Having 3 kids, having 4 kids at 16, it was just like, oh no, that's the worst. And this, we didn't have to worry about it, because we can figure it all out just with the rule without having to make any giant diagram. Now, last but not least, and this is a really important thing to note, the word and. So if you look at these rules, these 2 rules both have and, E and F, E1 and E2 and so on. But that word and is often hidden. In English language, we often find ways to get out of saying and. So that means that we're going to need to pay close attention to the English that's used. So when they things like both, Both of these people have to be successful. Both of these people have to be certificate. Or all of these people, see this word all of these people are associate in applied science. That was an implied and right there. Right? I didn't say and, it just was. All three of these people are associate in applied science. None of these people are associate in arts. You see what I'm saying? So that word and in the English language is often hidden by numbers, both, all, none. So watch out for this. Put this on your note sheet for the exam. Warning, 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 right? They will be sneaky on you. Right. In general, if you're dealing with more than one thing in sequence, two people, three people, two rolls of the dice, three rolls of the dice, five rolls of, or five draws of the lottery, etc., it's going to use the multiplication rule. It just will. So be prepared for that.